Hello students, welcome to EPG Pathshala. I am Rashmi Sinha from Indira Gandhi National Open University. Today, we are going to talk on module Adaptation of Growth Rates to Cold Stress in the paper Human Growth and Development. Now, what are we going to learn in this module? We'll find out how human adults physiologically respond to both chronic and acute cold stress. Second, we'll determine the physiological processes of newborn infants in cold stress. We'll also examine the adaptive responses of human growth rates to cold stress, find out how humans acclimatize to cold climates. We'll also list out the individual factors that determine tolerance to cold stress and understand how man adapts himself in cold water. Now, what is adaptation? Adaptation is a process of physiological, genetic, and biochemical modification to a particular environment and or stress in order to survive and reproduce. It involves 5 levels: genetic adaptation, which evolution of advantageous characteristics; developmental adaptation or plasticity, which is acquiring of appropriate responses in a particular environment during growth; and long-term acclimatization, which is acquired over years but reversible during changes to the environmental; seasonal acclimatization, these are the changes reversible annually; and short-term acclimatization, that is the daily or irregular responses to the changes which happen. The rate of growth is affected both by intrinsinic, which is the genetic, and extrinsic, which is environmental factors. In the mid 20th century, slower maturation and reduced growth, which were responses to physical environment, were considered adaptive. Since 1960s, the theory that growth is a way for humans to adapt to their immediate surrounding has been there. This theory is different from the view that slow growth is the direct effect of adverse conditions like socioeconomic status or dietary pattern. Thus, researchers used two contradictory interpretations of growth pattern influenced by environment. Cold climate is one of the physical environmental factors affecting growth rate, which is interpreted in an adaptive framework. In man's life, he is particularly susceptible to cold stress during the few months after birth and old age. This module discusses the effect of cold stress on human growth rate, physiological responses with which man has counteract such stress, the individual factors that modify and affect these responses, and the process of acclimatization to cold stress. Physiological responses to chronic cold stress. Adaptive changes. Physiological responses to cold are dependent upon the age and the physical fitness of the concerned individual, intensity and duration of exposure to cold temperature. The amount of insulation determines the degree of cold stress. The moderate cold stress experienced for prolonged period of time, either seasonally or throughout the year, is referred to as chronic cold stress. During prolonged cold exposure, homeothermy can be maintained by two mechanisms. One, enhancement of metabolic process, which increases heat production, it is the metabolic adaptation; and two, the insulative adaptation, in which the increased insulation or its correlates to decrease heat loss. Metabolic adaptation to cold. Non-shivering cold thermogenesis, localized mainly in brown adipose tissue, is developed, and less economical shivering thermogenesis is gradually replaced for increased tolerance to severe cold. Changes in secretion, release and physiological effects of catecholamines with non-adrenaline causes greater heat production. Insulative adaptation to cold. Cold acclimatization in man is done by an increase in the thickness of subcutaneous fat which acts as an insulating agent. Hypothermic cold adaptation. Hypothermic cold adaptation involves the development of hypothermia, that is, reduced thermogenic response to cold due to shift of the threshold for cold defense reactions to the lower levels of skin and cervical spinal cord temperatures. This may be caused when an individual is attributed to repeated cold stimuli. This results in a decrease in core body temperature and reduced shivering. Reduced shivering is more economical and it increases cold tolerance. This kind of cold adaptation can be found among the Amas and Australian Aborigines. Physiological effect of acute cold stress. When an individual is subjected to severe cold stress for short periods of time, then such kind of cold stress is referred to as acute. Changes in the body heat loss. Core temperature is maintained at higher level than surrounding environment, but since heat is lost from the surface of the body, the skin is cooler than the core of the body. This gradient of temperature between the core of the body and the skin can be modified by altering insulation of the skin and the tissues in order to regulate heat loss by convection and conduction. Insulation of the tissue is determined by thickness of the skin and subcutaneous fat and the rate of blood flow in the tissues. Now, chronic or repeated cold stress. Does it lead us to body heat loss? If no, then there is cold habituation, in which case there will be blunted shivering and blunted cutaneous vasoconstriction. But in case there is a body heat loss, then there is an increased metabolic heat production sufficient to defend body temperature. If this is so, then the metabolic acclimatization or acclimation takes place, which enhances shivering thermogenesis and also enhances non-shivering thermogenesis. If increased metabolic heat production sufficient to defend body temperature is not there, then insulative acclimatization or acclimation is there. In this case, enhanced cutaneous vasoconstriction and improved muscle blood flow towards subcutaneous shell is observed. Vasoconstriction. Now, what is vasoconstriction? When an individual is subjected to a temperature of 0 degrees or even 15 degrees Celsius, subcutaneous blood vessels are constricted to reduce the cutaneous blood flow. Vasoconstriction directs the flow of venous blood through the veins that are close to the arteries. As such, arterial blood entering the limb at a high temperature comes in contact with cooled venous blood. A countercurrent heat exchange establishes across the walls from the arteries and the veins. This mechanism helps in decreasing the skin temperature and conserves the metabolic heat and the body core, thereby less heat is lost. People suffering from Raynaud's disease or anoxia nervosa have local defect in their blood vessels and hence they exhibit an increased vasoreactivity to cold environment. Vasoconstriction is produced by the efferent sympathetic nerves and this sympathetic stimulation can be reinforced by cooling of the skin. Vasodilation. When the skin temperature falls below 10 degrees Celsius, blood vessels in the hands and feet dilate frequently, which is referred to as vasodilation. This occurs when the body core is warm and the extremities are exposed to cold. The cyclic phenomenon of the body, wherein the body alternates back and forth between vasoconstriction and vasodilation, compensate for risk created by both the mechanism, was first described by Lewis in 1930 and is known as Lewis-Hunting phenomena, which we can see it in the figure also. The intensity of hunting rhythm varies in healthy individuals. This shows the Lewis-Hunting phenomena. In this, you are showing the immersion of a finger in ice water and which illustrates how the intensity of the hunting rhythm varies in healthy individuals. Loss of heat from head and trunk. At 4 degrees Celsius, heat loss from the head accounts for one half of the total resting heat production. The facial skin, due to its close proximity to the thermal core areas, stabilizes well above freezing even under severe cold conditions, although facial circulation doesn't undergo vasoconstriction. By physical conductance, heat is transferred from deep tissues and organs to the body surface. Therefore, a person immersed in cold water loses little heat from the extremities and more heat from the trunk due to high tissue conductance in the area. A protective layer, subcutaneous fat. Subcutaneous fat reduces heat loss from the body and cools the body core and extends the thermal metabolic responses to cold. The minimum core temperature of a body when exposed to 10 degrees Celsius or 15 degrees Celsius has been found to be positively associated to body fat percentage, which is indicative of less cooling ability in obese individuals than lean ones. An inverse correlation was seen between the skin temperature and the body fat percentage. Body fat plays an active role in the metabolic reaction to cold, as it is observed that lowering of respiratory quotient with duration of cold exposure is more in obese than in lean individuals. Now this shows the distribution of brown adipose and white adipose tissues in adults. You can see the brown fat tissue and the white fat tissues. Shivering thermogenesis. The body tries to adapt to cold stress by increasing the rate of heat production through shivering when the vasoregulatory mechanisms are not sufficient to counteract the heat loss. Shivering refers to involuntary contractions of the skeletal muscles throughout the body for regulating heat production when exposed to cold surrounding for a long time. The primary muscle response to cold exposure is termed as pre-shivering or thermal muscle tone. Both pre-shivering and shivering contractions appear first in the extensor muscles of upper limbs and the trunk, followed by extremities. Magnitude of shivering. Now what it could be? While shivering, the average increase in metabolism is 4 to 5 times the level of basal metabolic rate, which can be written also as BMR. Physical fitness, body size, insulation, etc. are the factors responsible for the onset and intensity of shivering. It is suppressed by physical exercise, that is voluntary muscle contraction, although this does not occur when body temperature is reduced. Control of shivering. Neurons activated by the stimulation of cold receptors controls shivering. This primary center involved in controlling shivering is located in the dorsomedial posterior hypothalamus. Secondary centers are ventrolateral posterior hypothalamus, ventromedial forebrain septums, ventromedial preoptic regions of anterior hypothalamus, and some points of cerebral cortex. Cooling and warming of the spinal cord evokes shivering and reduces shivering respectively. Physiological responses to cold in infants. An infant is exposed to severe cold stress at the moment of birth as he is delivered naked to the extrauterine environment from the warm maternal environment. A newborn responds to the cold temperature by vasoconstriction and then by non-shivering heat production. Thin skin, high body surface to mass index, scanty subcutaneous fat, inability to shiver, and very poor motor development accounts for thermal instability of the newborn babies. Metabolic changes after birth. An increase in the weight of metabolically active tissues in relation to weight of the body with reduction in the extracellular body fluid volume may be the factor for rapid increase in metabolism within the first few days of life after birth. An infant produces heat by metabolizing his carbohydrate and fat stores. The infant's liver glycogen is completely exhausted within few hours following birth, and blood glucose concentration falls very low. Metabolic responses in newborn babies. During the first 12 hours after birth, the metabolic response to cold is very light as compared to infants more than 4 days old. All babies become very active at very low temperature, but their rectal temperature falls at a rate of 1 degree Celsius per hour. This indicates that a baby left unclothed at a room temperature may become hypothermic. Even clothed babies may increase heat production to compensate the cooling of uncovered faces or for cool air that is breathed in. Mechanism of thermogenesis of brown adipose tissue. Uncoupling of oxidation with ATP synthesis in the brown adipose tissue generates heat. It is controlled by the central nervous system. Heat production in the tissue is enhanced by the interaction of non-adrenaline and beta-adrenergic receptors of brown adipose membrane. Factors affecting the amount of brown adipose tissues in newborns. Thermogenic capacity of brown adipose tissue in newborn is enhanced by short periods of starvation towards the end of gestation period or feeding with a diet containing linoleic acid. Tolerance of cold in newborn is decreased when brown adipose tissue is reduced to prolonged maternal undernutrition. Adaptive responses of human growth rates to cold stress. Let's see that. Cold climate affects growth and development, body size and proportion. This can be expected as we can see the differences in the physique of man. Body size and proportions of warm-blooded polytypic animals are related to temperature according to Allen's and Bergman's rule. Allen's rule states that longer extremities relative to body size are found in warmer climates and vice versa in colder climates, while Bergman's rule states that a larger body size is expected in colder than warmer temperatures. A delay in skeletal age, that is, a difference about a year in adolescence, is seen among the people living in hot regions due to their linear build. People in colder climates are found to be heavier with larger trunks and shorter legs. Rates of weight gain is fastest in winter. Greatest increase in weight often is in September through November. This seasonal rhythm is not established on children until they are 2 years old. However, this seasonal trend doesn't conform to individual growth patterns due to differences in endocrine reactivity. But climate seems to have minor effect on overall human growth rate. Few studies have examined the relationship of growth patterns to temperature. Each major race of mankind differ in stature according to the climatic conditions they are subjected to live. Growth variation during different seasons have been observed. A longitudinal study suggested that 30% of children have increase and decrease of growth velocity cycles dependent on season, while the remaining children showed growth acceleration and deceleration which could not be associated with seasons. Body's thermoregulatory process can be used to explain the relationship between body proportion and the temperature of the environment. In cold environment, the heat retention is vital to avoid hypothermia, hence less body surface area is more essential. Krogner studied the relationship between anthropometric measurements and climate in East African, Middle Eastern, and European population and found out that low temperature was correlated with cranial measurements. He said that it could be due to the capability of brachycephalic head shape to retain more heat in colder climates, but this argument could not be accounted for the correlation as cultural practices to protect the head such as hat were present. Boas also found out that the shape of the skull is plastic and can be changed only in a single generation. At the end of 19th century, children of immigrants to the US were found to have a different head shape than their parents. Malina and Bouchard suggested that growth in cold climate is shortened due to the relationship between a sturdy body type and early maturation. Bogan studied growth patterns in height of children in Guatemala and found that pre-adolescent boys and girls and post-adolescent boys showed a seasonal pattern while adolescent children do not. Some studies had suggested that seasonal rhythm of weight gain exists in children. Lower incidences of menarche were observed in Finland and South Africa during the winter months. A study on children and adolescents in response to exercise in cold was conducted among club swimmers in a pool at 20.3 degrees Celsius, and it was observed that the rate of cooling decreased with age in both the gender. Children and less subcutaneous insulation with the large surface to body weight ratio had the fastest rate of cooling. Figure. Here you can see the artificial adaptation to cold stress among the inhabitants of cold regions, how they're wearing the woolens hat and shoes. You can see the clothing and their head. The mongoloid phase. Coongard and Birdsell have hypothesized that mongoloid phase is adaptive of life in colder climates. People living in colder regions such as Arctic and North Asia have broad flat faces which help them in reducing the effects of frostbite. Brow ridges, frontal sinus and nasal prominence are reduced. Orbital and malar regions are also more flattened and widened to retain more layers of fat for additional warmth. Eyes. In the mongoloids, they have epicanthic fold, which is common among northern and eastern Asian population, and it is protective feature of the eye from the hard driving snow typical in these regions. Skin color. Also, the lighter skin is prevalent among the people living in the colder regions, as this allows the penetration of the sun's ultraviolet rays, which helps body in synthesizing vitamin D. Nose shape. Smaller, longer and narrower noses are generally found among the people in colder regions. This adaptive feature of the nose moistens and warms the incoming air because the vapor pressure helps in exchange of moisture between the respiratory surface and the air. The activity of the cilia of the nose is reduced more by drying than by heating or cooling. Under normal conditions, soot and bacteria are cleared in the respiratory tract through mucus secretion. The rate of mucus secretion is positively correlated with humidity of the inspired air. This sensitivity of the drying of respiratory epithelium could be the cause for high incidence of sinus and respiratory infections among the Eskimos. Let's come to hair now. Straight hair is mostly found in people living in colder climates as it keeps the neck and head warm and also allows cold moisture to run off the scalp more easily. Acclimatization to cold. Now let's see what could be that. Metabolic adaptation in man. Acclimatization means increased tolerance to cold. It develops gradually. Newcomers to Arctic region wear all their clothing in the beginning, but as winter approaches and temperature falls, they no longer sought any extra protection. Men who go for expeditions during winters were less at work than at the beginning. The members of such expedition who spent more time indoors were found to have suffered frostbites at low temperatures within 1.5 minutes, while those who spent more time outdoors resisted frostbite for nearly 10 minutes. Well-adapted individuals are keener in appreciating their lower limb and take necessary precautions to prevent frostbite. The rate of heat production is decreased in winter, as can be seen among the Norwegian, British and Swedish men. On the contrary, an increase in heat production in winter was observed among the Japanese, and lack of this response in Western people temporarily living in Japan was attributable to differences in diet, physical activity and body surface area. Eskimos also show larger increase in BMR than Europeans living in the same cool environment. An increase in BMR in winter also occurs among the Koreans Amas who dive throughout the year wearing suits.
BMR as a defense mechanism against body cooling in water seems to be less important. It remains uncertain that metabolic alterations depends on direct cold exposure or endocrine function or on peculiarities of diet, but may depend on stimulation of sympathetic activities. In this, we can see the comparison of shivering thresholds in different control Koreans, women, and men with Korean amas. Fat is perhaps more important than protein in exerting an adaptive response to cold. This kind of insulative adaptation can be directly related to the channel swimmers. Inhabitants living in Arctic region consume large quantity of fat in order to keep their bodies warm. In conditions of severe exposure, increase in production of heat reduces the fall of the rectal temperature. This allows the skin temperature to rise, thereby bringing in comfort to the individual under cold stress. This shows the thermal responses to skin cooling in representatives of various ethnic groups. This was a study. This is taken from Lee Bank, 1975.
Local cold exposure. Local acclimatization is prevalent among Eskimos, Arctic Indians, fishermen, lumbermen, etc. Men living or working in cold climate expose their hands and face more than parts of the clothed body. It has been found that people who habitually expose their hands to cold respond to local cooling of their hands by less vasoconstriction and rapid vasodilation than unacclimatized individuals. Cooling of hands reduces numbness and preserves the dexterity of the hand. It also causes elevation of blood pressure and increase in heart rate. Local face cooling also occurs wherein there is decrease in heart rate and elevation of blood pressure, leading to a condition known as bradycardia. However, such a response could impose an extra load on the heart, producing ischemia. A group of participants were kept in cold room for 2 hours a day, 5 days a week for 5 weeks, and at 15 degrees Celsius with heavy clothing but no hand gloves. They showed reduced tactile discrimination, but the outdoor group scored higher on tactile discrimination than the indoor group. This points to a greater resting finger and blood flow in the hand of habituated group. Hence, cold acclimatization can be acquired.
The Central Australian Aborigines sleep naked at about 0 degrees Celsius and minus 45 degrees Celsius. Under the same conditions, the field investigators were unable to sleep due to shivering and low skin temperatures. Similarly, the Bushmen of Kalahari sleep under the same extreme cold climate with single covering and a small fire. Europeans can attain a high degree of cold tolerance. Norwegian students who stayed in the open for 6 weeks could not sleep with minimal exterior insulation but were able to sleep later. Eskimos have greater tolerance to cold in the hands than the Europeans. Eskimo, Indian, Negro, and European participants were immersed in water near freezing point. Negroes revealed a greater propensity to frostbite, which was attributed to their experience in the Korean War. Ability of acclimatized man to use their hands efficiently is related to increased flow of blood. Tolerance to cold. Individual factors. Heat transfer follows Fourier law, which states that the heat loss per minute is directly proportional to the surface of the body, the difference between temperature of the body and the environment. Surface area. The heat required to maintain homeostasis will be greater in small than large individuals because the surface area is greater per unit of body weight when the total body water is smaller. Same principle applies to children as well. A significant negative correlation between rectal temperatures and the measurements of hand and foot size of highland Peruvian Quinchua Indians were observed when hands and feet were exposed for 2 hours at 10 degrees Celsius. Insulation of fat. The most important factor for heat loss is the degree of natural or artificial insulation. The thermal conductivity of subcutaneous fat is less than the muscle since it is not vascularized. Due to this reason, the gradient between body's surface temperature and the environment is smaller when the fat layer is greater. Thin individuals have increased heat production when immersed in cold water because of fat insulation. Survival in cold water depends on amount of subcutaneous fat and artificial insulation, for example, clothing. The effectiveness of subcutaneous fat depends on physical activity. Individuals having the same fat thickness who were swimming experienced a greater fall in rectal temperatures than those who were at rest. This heat loss from activity could be detrimental for individuals with high fat layer for human survival in cold water. Gender. One would expect that under cold stress, women's internal body temperature would be more stable than men as they tend to be fatter than men. But since women usually have lower body weight and high ratio of surface area to weight than men, they have more areas for heat loss, heat producing capability. Exercise. At a given water temperature during exercise, both men and women maintain same thermoregulatory responses, and these benefits were due to the added heat production from physical activity. Physical fitness. 17 healthy male volunteers were exposed to cold stress at 1, 5 and 10 degrees Celsius, and it was observed that the production of heat was directly correlated with maximal oxygen uptake. Maximal oxygen uptake is the peak value of oxygen consumption by an exerciser at the point of exhaustion or fatigue. This implies that fat individuals have more efficient thermoregulatory mechanism against cold stress than unfit individuals. Age. All the thermoregulatory responses can be triggered instantly after birth, even in premature babies. Without shivering, their heat production can be increased 100 to 200% above the resting metabolic rate. But due to larger surface area to volume ratio of newborns than adults, vasoconstriction is not as effective in adults for reducing heat loss. Thus, if thermal balance has to be maintained at low metabolic rate in newborn, then the temperature must be 32 to 34 degrees Celsius than adults. Thermoregulatory responses are better in young adulthood than in old age as measured by responses of the fingers of the hand. Cold-induced vasodilation of the fingers and the hunting waves are more rapid in no adult individuals than other adult individuals. Recently, men from 22 to 73 years were exposed to 10, 15, and 20 and 28 degrees Celsius temperature. It was observed that older men have increased metabolic rate than the younger adults, indicating that older people are more susceptible to cold stress than young individuals.
Now let us learn something about man in cold water. Man can stay in a very narrow temperature ranges in water as compared to air without experiencing excessive cooling because the thermal conductivity and specific heat of water is 25 times and 4000 times greater than the value of air respectively. Hence, a nude man will have difficulty in reducing heat loss in water even at a moderate temperature, which can be 20 to 25 degrees Celsius. The cold stress produced by the aquatic environment may become so severe and become life-threatening too. The most vital factor determining the variability in cooling rate in water is the thickness of the subcutaneous fat. As obese person cools at a slower rate than the lean person, and it can be a matter of life and death when immersed in water. Thermal balance in water is maintained by an increase in heat production by shivering.
Heat conductance to the skin is increased due to increase in blood flow during shivering or voluntary muscular contraction. This elevates the heat loss, which is proportional to the difference between the temperature of the body core and the water. Heat loss by convection also doubles due to increased water turbulence created by the movement of the body during swimming. Individuals who worked at moderate intensity in cold water have an increased body temperature than when they worked as hard as possible. But maximum work can be performed only for a short period of time. The lean child cools very rapidly in water at 20 degrees Celsius due to large surface area of the skin per mass of the body facilitates heat loss from this body. In many regions of the world, swimming is common in 20 degrees Celsius. However, this may pose a risk for small, lean young swimmers who have not developed cold defense.
Let us summarize what we learnt in this module. Adaptation is the process in physiological, genetic, and biochemical modification in a particular environment and or stress in order to survive and reproduce. It involves 5 levels: genetic adaptation, developmental adaptation or plasticity, long-term acclimatization, seasonal acclimatization, and short-term acclimatization. Cold climate is one of the physical environmental factors affecting growth rate, which is interpreted in an adaptive framework. The moderate cold stress experienced for prolonged period of time, either seasonally or throughout the year, is referred to as chronic cold stress. During prolonged cold exposure, homeothermy can be maintained by two mechanisms: enhancement of metabolic process, which increases heat production, metabolic adaptation, and increased insulation, or it correlates to decreased heat loss, which is insulative adaptation. Allen's rule stands that longer extremities relative to body size are found in warmer climates and vice versa in colder climates. While Berkman's rule states that in larger body size is expected in colder than warmer temperature, people in colder climates are found to be heavier with larger trunk and shorter legs. Acclimatization means increased tolerance to cold and it develops gradually. Newcomers to Arctic region wear all their clothing in the beginning, but as the winter approaches and temperature falls, they no longer sought any extra protection. It has been found that people who habitually expose their hands in cold respond to local cooling of their hands by less vasoconstriction and rapid vasodilation than unacclimatized individuals. Individual factors response for tolerance to cold are body surface area, insulation of, thickness of the fat, gender, exercise, physical fitness and age. Thank you.